So last time we learned that if molecules are going to be created with their shapes predicted from the VSEPR theory, they actually don't bond with their outer shell s and p orbitals. You know that p orbitals exist on the x, y, and z axis. Those are 90 degrees apart from each other. If you use p orbitals to bond, you're going to get molecules whose bond angles are 90. Yet experimentally, we find that bond angles in molecules tend to be more like things like 109.5. So that means central atoms cannot be bonding with their s and p orbitals in their outer shell. It was Linus Pauling that made a proposition as to what must really be happening. These atoms are taking their valence orbitals, usually their s, px, py, and pz, and they're hybridizing them. They're creating 4 brand new atomic orbitals that are called sp3 orbitals. And when he took the wave functions for those newly created sp3 orbitals and graphed them, those orbitals pointed to the 4 corners of a tetrahedron, which means that if other atoms bonded to those orbitals, you would wind up having bond angles of 109.5, which is what we see experimentally. So when we talked about yesterday water, ammonia, and methane, those molecules must have their central atoms undergoing sp3 hybridization so that when the hydrogens bond to either oxygen, nitrogen, or carbon, they form tetrahedral angles, 109.5, between the attached hydrogens. We're going to look at some other molecules that are maybe not necessarily tetrahedral today and see if we can explain how they exist. So the Bh3 molecule is an example of a molecule whose central atom does not achieve an octet because it's electron poor. This is actually the correct Lewis structure for Bh3. Boron does not achieve an octet. If we wanted to predict the shape of this molecule, we would go, well, that boron has a steric number of 3. And how do 3 groups spread themselves out as far apart as possible? It's a trigonal planar array. So we would think this actual molecule is a flat molecule that looks like a triangle with 120-degree angles between them. So how could this happen? Well, maybe the boron is going to undergo hybridization like the oxygen and the nitrogen and the carbon did yesterday. So if it undergoes, let's say, sp3 hybridization, it's going to take its s, px, py, and pz orbitals in its outer shell, and then it's going to wind up hybridizing them into sp3 orbitals, which point to the 4 corners of a tetrahedron. Let's see how that looks. Here's the arrangement of sp3 hybridized orbitals. So this boron is going to bond to 3 hydrogens. Why don't we pick 3 of those orbitals for the hydrogens to bond onto? One of those orbitals, I guess, will be empty. So let's say the hydrogens bond onto the bottom 3, and they bond here to create these bonds. What's the shape of that molecule? What shape have we created?
Looks like a pyramid.
It's exactly a pyramid. So if boron underwent sp3 hybridization, it would not form a trigonal planar molecule, which means flat, right? It would form a pyramid molecule, and the angle would be 109.5 because that's what sp3 hybridization is. But we know the real molecule Bh3 is flat and the angle is 120. That just means that boron cannot be bonding with sp3 orbitals. It certainly can't be bonding just with its px, py, and pz because then the bond angles would be 90 and that doesn't match 120. So it must be doing something else. So it turns out that when you have a central atom in a molecule that has a steric number of 3, like boron does here, it doesn't have to hybridize all 4 of its valence orbitals. It only has to hybridize 3 of them. And we're going to look and see what happens when boron hybridizes only 3 of its valence orbitals instead of all 4. So when I say it has 4 valence orbitals, these are them: a 2s, a 2px, a 2py, and a 2pz. Boron electron poor only has 3 valence electrons. That's why it's really only making 3 bonds and doesn't achieve an octet. So what we think is going to happen for boron is it's going to undergo hybridization. It's going to take its natural valence orbitals with the electrons 2 in the 2s, 1 in the 2px, and then nothing in the 2py or 2pz. And it's going to undergo hybridization, but we're not going to hybridize all 4 orbitals. So here's where you have to really pay careful attention to the picture here. There's 4 orbitals up there, 4 white orbitals, dashes for the orbitals here, right? We're going to only hybridize the 2s with the 2px and the 2py, only these 3. So those 3 will get scrambled together and they will create 3 orbitals that are of equal energy that are degenerate. So you're going to see 1, 2, 3 orbitals over here. And you see this one? We're not going to hybridize that. That means it remains unchanged. So over here, I'm still going to have a 2p orbital left over, okay? So if I only hybridize 3 out of the 4 orbitals, I will get 3 degenerate orbitals, those are the 3 orange dashes, and the 2pz orbital, which we are not hybridizing, remains exactly how it was originally. Now, where are the 3 electrons in boron going to go? They're going to go in those 3 degenerate orbitals one at a time, and this is how boron's going to be able to make 3 bonds, because now it has in its outer shell 3 unpaired electrons, if that makes sense. Now, we have to now try to figure out what these orbitals are called and then how they exist spatially in relation to each other. Because we're mixing together an s orbital and 2p orbitals, these guys are called Sp2 hybrid orbitals. The name always tells you how many of the original atomic orbitals you're mixing together. And we're mixing 1 s and only 2 of the p's, so these new orange orbitals are called Sp2s. So down here in our picture at the bottom, the boron has 1 electron in an Sp2, another electron in an Sp2, another electron in an Sp2, and that blank side stands for the 2pz orbital, no electrons in that. So what do these Sp2 orbitals look like, and what directions do they point in spatially? This is really the big $64 question. So here's our boron atom before it hybridizes. It has its natural 4 valence atomic orbitals, the round 2s, and then along the x-axis, the 2px in red, along the y-axis, the 2py in orange, and along the z-axis, the 2pz in purple. I'm not going to hybridize the 2pz, so when I show you my new picture after hybridization, you're going to still see the purple 2pz orbital pointing straight up and down. A thing to kind of recognize here is that the orbitals we are mixing together are the big old spherical 2s, and then the 2px and the 2py, which are all in the xy plane. So it might make sense that when we create the hybrid orbitals, those Sp2 hybrid orbitals are going to be in the xy plane, and in fact they are. And it turns out that those Sp2 hybrid orbitals point on the xy plane in a trigonal planar geometry, 120 degrees, 120 degrees, 120 degrees from each other. If I draw the trigonal planar triangle there for you to see, these are the Sp2 orbitals that would be predicted if you actually graph their wave functions from the Schrödinger equation wave functions. So when you actually have Sp2 hybridization, you do create 3 hybrid orbitals that fortuitously point in the 3 corners of a perfect equilateral triangle, which means their angles are 120 degrees. And you see where that purple 2pz orbital is? It has 1 lobe pointing above the triangle and 1 lobe pointing below the triangle. So it sticks above and below the plane of the Sp2s, which are on the xy plane. So the angle between the Sp2 hybrid orbitals here turns out to be 120 degrees. And if you look at the 2pz orbital, you should see that 1 lobe is above the triangle, 1 lobe is below the triangle. So we say the 2pz orbital is 90 degrees from the plane of the Sp2 hybrid orbitals, 90 degrees up and 90 degrees down. Now, that picture on the very right side that shows my Sp2 orbitals and the 2pz, I want to take that picture, I want to tilt it towards me 90 degrees, okay? So if I rotate this towards me 90 degrees, the 2pz, which right now is pointing straight up and down, if I tilt it towards me 90 degrees, it's going to be pointing directly at me. So I just want you to see this alternate perspective. If the 2pz is pointing directly at me, that means the plane, that triangle plane of the Sp2s, will now be flat on the plane of the paper. So this is what you want to see if you can really realize what's happening. Tilting this 90 degrees towards me means the 2pz, which was originally just pointing straight up, is now pointing straight at you. And you can see the big purple lobe right here pointing at you, and there's the big purple lobe behind it going behind the plane of the paper. What happens to this triangle? This is on the xy plane. So when you tilt this towards you 90 degrees, it's now flat on the paper, and you see the perfect equilateral triangle flat on the paper there. So that's 2 different perspectives of Sp2 hybridized atoms I want you to be able to see. It's a trigonal planar array of Sp2s. If you want to draw the 2pz on the plane of the paper like this, then the Sp2s are on this plane that's not on the plane of the paper. It's actually sticking out towards you. It's perpendicular to that. But if you rotate this towards you, now the pz orbital is pointing towards you, and the Sp2s are flat on the page, okay? So if this is actually what boron does, then boron would have one electron in each of the sp2 orbitals. Those sp2 orbitals now will be able to bond with hydrogen atoms that have electrons in their 1s orbitals. So if I bring my hydrogen atoms with their 1 electron each in their 1s orbitals and make them overlap, we'll form a bond between each of those. If we rotate this towards us, you might be able to see the shape a little bit more clearly. What's the shape of this molecule? Boron attached to hydrogen, hydrogen, hydrogen. That's trigonal planar. So it looks like our explanation for why Bh3 forms a trigonal planar molecule with 120-degree angles is because it only needs 3 orbitals to hybridize to make a steric number of 3. So it hybridized the s, one of the p's, and a second of the p's. SPP, Sp2 hybridization. And as we found out when we graphed the quantum mechanical wave functions, Sp2 orbitals point exactly in this trigonal planar geometry. And so they must be the orbitals being used to create this molecule. Okay? So you form a bond here, form a bond here, form a bond here. Okay? So we wind up getting a trigonal planar molecule in which the bond angle between the red and the orange bond, between the orange and the yellow, between the yellow and the red, those angles are all 120 degrees. Now, can we name the bonds here? These bonds, if you draw an internuclear axis, are completely symmetrical, so that means they're going to be called sigma bonds. And then what are the 2 orbitals that are merging together to make the bond? Let's take the red one. What orbital was this originally? That was the hydrogen 1s. What orbital is this? That was that newly created sp2 orbital. So this bond would be called a sigma sp2 plus 1s. And each of the bonds in this Bh3 molecule would be named the same way. So anytime you have a central atom that has a steric number of 2, we believe, a steric number of 3, we believe it's only hybridizing 3 of its valence orbitals. It would always hybridize the s, and the remaining number of p's would be 2 of them. So you would get sp2 hybrid orbitals, which you now need to know form a trigonal planar geometry. This shouldn't be so complex. Yesterday, we did a whole bunch of atoms with steric numbers of 4. So they hybridized all of their valence shell, the s, the px, py, and pz. They hybridized an s and 3 p's. That's what you get from steric number 4. If you know a steric number 4 makes a tetrahedron, you now know the geometry of sp3 orbitals. They're tetrahedral. Likewise today, if you have an atom that's has a steric number of 3, it's going to only hybridize 3 orbitals, an s and 2 p's. So those hybrid orbitals will be called sp2s. And because they come from a steric number of 3, which you know is trigonal planar, the sp2 orbitals have to be trigonal planar as well. Okay.
That was for steric number 3, correct, Professor?
That's for steric number 3. So yesterday we did steric number 4. Now we just gone over steric number 3. Let me now go over steric number 2. If you have another molecule with a central atom that does not quite make an octet, and that would be beryllium. Beryllium forms the molecule with 2 hydrogen atoms that would have a Lewis structure that would look like this. In this particular case here, the steric number of the central atom is 2. And so we would predict, gee, what would be the shape based upon BSEPR theory? 2 things spread themselves out as far apart as possible as a line. So we would predict this molecule would be linear. If you want to draw its picture, it would look like this. So how could that be happening? It might be undergoing sp3 hybridization, but wait a second, if you underwent sp3 hybridization and the beryllium used its sp3 orbitals to bond to 2 hydrogens, what's the angle between sp3 hybrid orbitals? What would that angle be?
120?
That's for sp2 hybrid orbitals.
180?
It's not 180 for sp3s. sp3s forms the tetrahedral array. What's the tetrahedral angle?
90.
109?
109.5. So if it would have undergone sp3 hybridization, the sp3 orbitals were pointing to the 4 corners of a tetrahedron, and the angle in a tetrahedron is 109.5. Okay? Now, if it would have undergone sp2 hybridization like we just did, sp2 hybridization forms orbitals that are trigonal planar. So if it's sp3, you get bent 109.5. If it's sp2 hybridization, the sp2 hybrid orbitals are the ones that form the trigonal planar geometry. That's the angle that's 120 degrees. So you would get a bent molecule with an angle of 120 degrees. Somebody said 90 degrees a moment ago as to maybe what the angle was. That's what would happen if the beryllium bonded with its p orbitals, maybe a px and a py, because the px is on the x-axis, the py is on the y-axis. That would be a 90-degree angle. So I could have put that in here. What if it didn't hybridize at all and just bonded with a 2px and a 2py? What would the shape be? It would have been bent 90 degrees. But neither of these are correct, because this atom does not have a steric number of 4 or a steric number of 3. That's why it's not doing sp3 or sp2. It has a steric number of 2. So if the central atom has a steric number of 2, it doesn't have to hybridize 4 or 3 valence atomic orbitals. It only has to hybridize 2 of them. So we believe beryllium is only hybridizing its s orbital and one of its p orbitals. I'm going to probably pick the px. So let's take a look at what's going to happen if you undergo this type of hybridization, and then we'll see when we graph the wave functions what they actually look like and how they're arranged spatially. So here's the normal electron arrangement for the valence shell of beryllium. It has 2 electrons. They both go into the 2s orbital. If we believe it's going to only have to hybridize 2 orbitals, it'll hybridize the s orbital and then one of the p orbitals, and I'm going to have it hybridize the px. So these 2 will hybridize together, and because we're mixing 2 of them together, they're going to create 2 hybrid orbitals. See the 2py and the 2pz? They're not being hybridized, so they're going to stay in their unhybridized form over here on the right side. Okay? Now, the 2 electrons in beryllium right now, and this is what it would look like. You'd wind up having the 2 hybrid orbitals created, and then the 2py and the 2pz left over afterwards. Okay? Where do the 2 electrons go? They would go in the 2 degenerate orbitals, 1 in each, and this would allow the beryllium to actually make the 2 bonds. So beryllium naturally had 2 valence electrons in its 2s orbital, nothing in any of its 2p orbitals. But when it's undergone this type of hybridization here, you're actually causing the electrons to split up because they now go into those 2 hybrid orbitals. You want to tell me what the name of these hybrid orbitals probably is?
SP.
Exactly right. You may have said sp1, but they just say sp. So you're only hybridizing an s and a p, so that's the name of the orbitals. And so the 2 electrons in the dot notation for beryllium at the bottom right, those 2 electrons are in separate sp orbitals. And then what are the 2 blank spots on the right and the bottom of beryllium? That's the 2py and the 2pz because they're empty. So now, what is the geometrical arrangement of sp hybrid orbitals? This is going to tell us whether this is really the right answer or not, because we know the molecule in reality is linear. So let's hope that the sp orbitals wind up giving us a molecule that would be linear. So here again are the valence orbitals for a beryllium atom, for any atom really in the second row on the periodic table: spherical 2s, a red 2px, an orange 2py, and a purple 2pz. I'm only going to hybridize the 2s orbital, which is spherical, and then the red 2px. And because the 2px only goes along the x-axis, you might imagine the 2 hybrid orbitals might only be along the x-axis, because the purple 2pz is going to stay the same, and the orange 2py is going to stay the same because they're not being hybridized. And as it turns out, when we figure out what the arrangement geometrically are of the 2 hybrid orbitals created, they actually do point exactly on the x-axis. One of the sp orbitals points to the left on the x-axis. The other sp orbital points to the right on the x-axis. And you can see the purple and the orange orbitals here were unhybridized. They just are their original selves. So because these sp orbitals have a 180-degree angle between them, because one points to the left, one points to the right, then if you're going to actually bond with those 2 orbitals there, you're going to wind up having a molecule whose angle is 180. So these 2 orbitals lie on the x-axis. That's linear. So the sp hybrid orbitals are linear with an angle of 180 degrees between them. The other 2 unhybridized orbitals, the 2pz and the 2py, are both perpendicular to that, right? The 2pz is perpendicular up from the sp line, and the 2py is perpendicular back and forward from the sp line, just like the y-axis and z-axis and x-axis are all perpendicular to each other. So the 2py and the 2pz orbitals in this picture on the right are both 90 degrees from those sp hybrid orbitals. The 2pz's are 90 degrees up, and the 2py's are 90 degrees forward and back. So if we remember that the electrons in the beryllium atom are in the red and the yellow orbitals, the sp on the right and the sp on the left, those are the orbitals that are going to bond. So hydrogens are going to bond with the red and the yellow orbitals in this picture. And so when two hydrogen atoms come up with their single electron in their 1s orbitals, and they overlap with these sp hybrid orbitals, they will merge together to form a pair of bonds. And there's your molecule. It's a straight line. So if you undergo sp hybridization, you're going to get linear molecules, bond angle of 180 degrees. You want to tell me what the names of each of those bonds are? What do you think?
Sigma.
The
Sp+1s.
It's a sigma bond because if you draw the internuclear axis, they're perfectly symmetrical. The two orbitals overlapping are a 1s from the hydrogen and an sp orbital from the beryllium. So there's sigma sp plus 1s. Does that make sense? Is squiggly good?
yeah.
Okay. So this is what's going to happen anytime you have a central atom that has a steric number of 2. So here's your big pattern. Steric number 4, you hybridize all the valence orbitals, spp. You make sp3 hybrid orbitals. Steric number 3, you hybrid 3 orbitals. Just take your fingers, count them down. S, then P. So it's sp2. If your steric number is 2, as in the beryllium here, you only have to hybridize 2 orbitals, an S and a P, so you make sp hybrid orbitals. What are the shapes or geometries of sp3s, sp2s, and sps? It's exactly the same geometries as their steric numbers. Steric number 4 was tetrahedral, so sp3s are tetrahedral. Steric number 3 means trigonal planar, so sp2 orbitals are trigonal planar. Steric number 2 is linear, so sp orbitals are linear. It's an exact 100% correlation. Okay.
Professor, we said
Yes.
sp2 hybridizes s and p orbit. What does sp3 do?
sp3 hybridizes the s, the px, the py, and the pz.
Oh, yes, thank you.
All of them. That's where we get the name sp3. The name is telling you how many orbitals are being mixed together. So if they say sp3, they mean 1 s and 3 p's. Make
Thank you.
sense?
It always ascends in that order, X, Y, Z.
That's just random, but it doesn't really matter. But technically, that's how we do it.
Okay.
And sp4 hybridizes all orbitals.
You can't have an sp4 because there are not 4 p orbitals in an energy level. So you can have sp, sp2, sp3, right? If we take a look at this for a moment. So when you're in the outer shell, let's say a second period element, the orbitals in the second period in the outer shell are these, okay? So let's say you have a molecule whose central atom is steric number 4, another molecule whose central atom is steric number 3, another atom, steric number 2. You should know the shapes for each of these. Steric number 4 always makes tetrahedrals. Okay. Steric number 3 makes trigonal planar. And if you don't 100% know this, this is on the front page of that handout you're using to do the shapes of molecules.
Yeah, looking at it.
Okay. And this is linear. So watch this. If you have a steric number of 4, you have to hybridize 4 orbitals. Watch this. 1, 2, 3, 4. Okay? So that you're hybridizing those 4. How many S's did I hybridize? 1. How many P's did I hybridize?
3.
So we just don't draw the 1 there. So that means steric numbers of 4 make sp3 hybridized orbitals.
Thank you.
Okay? Now, let's go to steric number 3. If you have a steric number of 3, you're only going to hybridize 3 orbitals. You hybridize the s, the 2px, and the 2py. So you're hybridizing 1s orbital and you're hybridizing 2 p orbitals. Those are sp2s. Guess what their arrangement is? They're trigonal planar. Guess what the arrangement of sp3s were? They're tetrahedral. Does that follow?
Oh, yeah.
Finally, I need another color. If you're going to do steric number of 2, you only have to hybridize 2 orbitals. So we hybridize the S and the P. So you form sp hybrid orbitals, and guess how they're arranged in space? They're linear.
I get it now. Thank you very much, Professor.
So that's the pattern if you want to sort of have down. Let's see if I can get us back to where we were. I don't know if that did. Let's see if this does it. Okay, what is this? Okay, can you all see that? pH 5?
Yep.
Good. So let's try this molecule, pH 5, total of 10 valence electrons altogether. We draw the skeletal structure. We put phosphorus in the center. We're making 5 bonds to it. Oh no, that's not an octet. Oh, but wait a second. Phosphorus has d orbitals in its outer shell, so it can do this. So that's why it can exceed the octet rule. So this actually uses up to 10 valence electrons. I've got them all drawn. I can't put any lone pairs. And if I check the formal charge on the phosphorus, it's, let's see, 5 minus 5 minus 0. It's a formal charge of 0. This is our best structure, okay? So if the phosphorus is going to make 5 bonds, remember like a week or two ago, we told you why this could happen. It seems like an exception, right? It shouldn't happen. How do you exceed an octet? Well, it has extra orbitals in its outer shell. If you're going to have a central atom with a steric number 5, you need to have 5 valence atomic orbitals. And so I told you, oh, it uses its d orbital to bond. And nobody questioned me on that. I just sort of told it to you, but you believed it on blind faith. But that really wasn't very good of me to say. How is it using that d orbital? Well, this is how it's using it. It's going to hybridize a d orbital to create a set of hybrid orbitals so that you can make 5 bonds. And let me show you how that works, okay? So here's the natural outer shell of a phosphorus atom. Almost all phosphoruses will bond with their 3s and their 3p's. They have 5 electrons altogether, 2 in the 3s and 3 in the 3p like this, okay? But when you only have 4 orbitals, you can only make at most 4 bonds. You can't make any more than that, but pH 5 is making 5. So it must be using its d orbitals somehow. So I'm going to draw the d sublevel in here as well. The s sublevels always have 1 orbital. The p sublevels always have 3. The d sublevels always have 5. So I'm going to draw these 5 orbitals here. Now, if the steric number is 5, can you guess what the phosphorus is going to have to do? It's going to hybridize an S, a PX, a PY, a PZ. What's that add up to? That adds up to 4, right? And then a d orbital. You only have to hybridize 5 orbitals to make a steric number of 5. So you hybridize the S, the 3 P's, and 1 of the D's. That's what we're going to do. If we hybridize the S orbital, the 3 different 3 P's, and 1 of the 5 D's, how many orbitals will be left unhybridized?
4.
So you'll see those 4 3D orbitals at the very top in white, but I'm going to take the 3s wave function, the 3px, the 3py, the 3pz, and whatever this one is, the 3dxy, and combine their wave functions, divide by 5, and then I'm going to wind up getting 5 new orbitals of equal energy. Okay, those will be the 5 new hybrid orbitals. And then I did not hybridize 4 of the 3d orbitals, so I'm going to show them at the top. So look what the 5 electrons can do now, because you have 5 degenerate orbitals. Instead of being a pair in the 3s and only 3 unpaired electrons, they'll unpair 1, 1, 1, 1, 1. Now the phosphorus can make 5 bonds, okay? So these 5 hybrid orbitals that are created will have a name. You want to make a guess as to what the name is?
SP5?
You didn't.
Oh, wait. SPD?
What you said wouldn't be sp5. You didn't combine an s and 5 different p orbitals. What orbitals were you scrambling together?
Sp3d.
An s, p3, and then a d, right? sp3d. Those are the 5 orbitals you mix together to create 5 equal energy orbitals that I have drawn in orange over here on the right side. Mr. Osenian, that makes sense?
Absolutely.
So then you also have those 4 different orbitals left over at the very top that were not hybridized, all those other d orbitals. And so I'm just going to draw them up here. They're actually going to be empty. Okay. So now with these sp3d orbitals, 1 electron in each, the phosphorus is now primed to bond to 5 different atoms, in this case, 5 different hydrogens. So if you come up with the new wave functions for these sp3d orbitals, all 5 of them, guess what geometry they arrange themselves in around the nucleus of the phosphorus atom? You want to make an educated guess before I even show you the next slide?
Trigonal by
Um,
pyramidal.
Oh my goodness. So Mr. Holmes now is going, gee, when it was a steric number of 2, which we learned was linear, the sp orbitals came out linear. When it was a steric number of 3, the hybrid orbitals came out trigonal planar. When it was a steric number of 4, the hybrid orbitals came out tetrahedral. I wonder what's going to happen when it's a steric number of 5. It's going to turn out to be whatever the shape is for a steric number of 5. Exactly correct. So the orbitals wind up pointing to the 5 different corners of a trigonal bipyramidal geometry. Now there's also 4 extra 3D orbitals in the outer shell of the phosphorus, so I'm not going to draw those. That would just be a total nightmare. But these are the 5 orbitals that have electrons in them. So the phosphorus has 1 electron in every single one of those 5 different orbitals, each of them their own unique sp3d orbital. So if they each have 1 electron in them, they're all capable of bonding with some other atom. And in this case, they're all going to be capable of bonding to hydrogen atoms. And so the hydrogen's 1s orbitals, those spherical green 1s orbitals, will overlap with each of those sp3d orbitals that you see here, creating 1, 2, 3, 4, 5 bonds. And you wind up forming a trigonal bipyramidal molecule, as we would have predicted from the VSEPR theory. So what do you think is the name of each of these bonds?
Sigma sp3d plus sp2 and s. I don't know.
So these orbitals here, the red, the purple, the blue, the orange, and the yellow, those are sp3d hybrid orbitals. So you had that 2/3 right. You said sigma sp3d, but then you have to name the orbital here from the other atom. Okay, let's go back. What atoms are these? What atoms are trying to bond to the phosphorus? Hydrogens, right?
Yeah.
What orbital does hydrogen have its only electron in?
1s.
That's a 1s. So this is an sp3d orbital. That's a 1s orbital. So when they overlap and form a bond, it's going to be called a sigma sp3d plus 1s.
Oh, I see. Thank you.
Sense?
Professor, what happens if we're not bonding with a s orbital? The sp3ds are just...
So you could have something like this, and I'm just doing simple hydrogens here just because this tends to be a little bit on the bizarre side for people, so I just want to make it simple at first. But let me tell you, let's say you had something like PF5, okay? So the phosphorus is bonding with fluorines, not hydrogens. The phosphorus is going to have a steric number of 5, which means it's going to undergo sp3d hybridization. So my phosphorus atom will have sp3d orbitals that look like this, pointing at the 5 corners of a trigonal bipyramidal geometry. Does that make sense?
Yeah.
They're all sp3ds. So let's do the Lewis structure for this because you need to be able to see this. If it's bonding to fluorines instead of hydrogens, this will make the picture more complex, and without a doubt, but it's not like impossible to figure out. And we'll actually be doing this within a week or so, so you'll have to be used to this anyway. So here's the arrangement of this, okay? So we're going to bond to a fluorine atom. So take a look at a fluorine atom. What's the steric number of that fluorine atom?
The steric number is 4.
So what kind of hybridization would the fluorine undergo if it has a steric number of 4?
It would undergo sp3 hybridization.
And what's the shape of sp3 hybrid orbitals?
Trigonal.
The dumbbell
Steric number, think about steric number of 4. What geometry do you get for steric number of 4? That'll be the geometry of the sp3.
Tetrahedral.
Tetrahedral. Does that make sense?
Yeah.
So here's my fluorine. So watch this. It's going to have 4 sp3 orbitals in a tetrahedron. Can you draw a tetrahedron? Watch this. 1, 2, 3, 4. This is like the one on the paper. This is the one on the paper, right? At 909-degree angle, coming out towards you, going back. Lone pair, lone pair, lone pair. That's the 3 lone pairs. The 1 electron here, and then each of those fluorines had 1 electron in their orbital. So the fluorines will bond to all the spots, but here's your bond. And you see what that bond's going to be? It's an overlap of an sp3d with an sp3. So the bond here would be sigma sp3d plus sp3.
Okay.
Now that works?
Yeah.
Now that was a little bit advanced. For most of us, that may have made today a whole lot worse than it helped, but that's actually really what happens, okay? So every single atom in a molecule, if you can determine its steric number, you can tell its hybridization. And then if you know the geometry of those hybrid orbitals, like you had to know sp3 was tetrahedral because it came from a steric number 4, then you should be able to draw those orbitals, and you just try to overlap the orbitals together like I did right here, and that makes the bond, and you just name the bond by just naming the two orbitals that overlapped.
Okay.
Okay? Okay. All right. So if that makes sense, let's try one more. Let's try SH6. If you wanted to draw the Lewis structure of this, there's actually going to be 12 valence electrons altogether. The skeletal structure would put sulfur in the center, 4 hydrogens bonded to it. When we do the skeletal structure, this actually has 12 electrons. I can't add any more, so I'm done. If you want to check the formal charge on the sulfur, you can tell it's 6 minus 6 minus 0 equals 0. So this is the best Lewis representation for SH6. What shape do you believe this molecule is going to wind up being? If we did experimental measurements on it, because it has a steric number of 6, well, and no lone pairs, we would expect it to be an octahedral molecule, which it is. So now we got to try to understand how are the valence orbitals of sulfur allowing it to make an octahedral molecule. Well, the whole key for yesterday and today is figure out the steric number, because that's going to tell you what kind of hybridization sulfur is going to need to undergo. Because if you're making a steric number of 6, then that means sulfur is going to have to hybridize 6 of its valence orbitals. So anytime you have a central atom with a steric number of 6, it'll need to hybridize 6 orbitals. Steric number 5 needs to hybridize 5 orbitals. Steric number 4 needs to hybridize 4. Steric number 3 needs to hybridize 3 orbitals. Steric number 2 needs to hybridize 2. It's always that way. So the natural outer shell orbitals of sulfur are the 3s and the 3p. Most sulfur atoms do their bonding only with the 3s and the 3p. But unfortunately, the 3s and the 3p, there's only 4 orbitals there. You can't bond to 6 atoms. You would need 6 orbitals to do that. So this is going to be insufficient. So sulfur has 6 electrons, but they're only in 4 different orbitals. In order to make more than 4 bonds to have a steric number greater than 4, you need to use another sublevel. And sulfur fortunately has the 3d sublevel like this, okay? And if you've been watching the pattern, you might be able to predict what I'm going to draw on the left side of this picture before I actually do that. So if sulfur is going to need to form 6 hybrid orbitals because it's steric number 6, you're going to hybridize the s, the px, the py, the pz, and then how many d orbitals?
2.
Yes, because that would add up to 6. So the 3s, 3px, 3py, 3pz, and then 2 of the d's will be combined together to form 6 equal energy orbitals like this. And then the 6 electrons in the sulfur will now be able to spread out over those 6 degenerate orbitals, 1, 1, 1, 1, 1, 1. Okay? And what are those orbitals called?
Sp3D2.
Sp3D2, because you mix together an S, all 3 of the P's, and 2 of the D's. And what's left off in my picture that I need to add on the right side there?
Empty d orbitals.
How many?
3.
Muy bien. Yes, exactly right. So we're not going to do the wave functions to try to solve for them with quantum mechanics. But what do you think? Those 6 different sp3d2 orbitals, how do you think they were arranged spatially with respect to each other? Squiggly?
With 90 degrees between them.
They would form an octahedron, just like you shape of SH6. So they're going to have 90 degrees between them, exactly right. So you would have an sp3d2 in red pointing to the right, an sp3d2 pointing to the left in yellow. Those would be 180 degrees apart from each other. but then they'll be 90 degrees away from the ones up and down, the purple sp3d2 pointing up and the blue sp3d2 pointing down. And then each of those are 90 degrees away from the orange sp3d2 pointing towards you, and then the more lavender kind of sp3d2 pointing to the back. Does that make sense? It's not a whole, you're not really memorizing a whole lot more. If you knew a steric number of 6 was octahedral, and you can now figure out steric number of 6 means hybridized 6 orbitals, so all you have to do is count the s, the px, the py, the pz, that adds up to 4, and then you need 2 more d's, then sp3d2 hybrid orbitals have to be in the same shape as steric number of 6. They have to be octahedral. So now when the hydrogen atoms come and overlap with each of those sp3d2 orbitals, then you wind up creating a molecule that forms an octahedral shape. And then see if you can actually name the bonds. It will take 30 seconds. We'll give you the answer and see if your name matches mine.
Wouldn't it be sp3d2 plus 1s?
Sigma sp3d2 plus 1s would be the name of each one of those 6 bonds in this molecule. Exactly correct.
So the purple and the blue are pointing up and down, and
Those are 2 separate orbitals. Yes, they're 2
yeah,
separate
and then the orange, yellow, and red, those are the equatorial ones.
So when you have a steric number of 6, you really don't have equatorial and axial, but according to how you're looking at it, yes. The yellow, the orange, the red, and that other color behind, those are like in the equator. And the purple's
Okay.
pointing up to the North Pole and the blue's pointing down to the South Pole. Exactly correct.
And then if you turn back to us, that would make the purple and blue like, okay, yeah, I got it
Tilting
now.
towards you, the purple would point towards you, the light blue would point behind, and then all the other ones, the yellow, the orange, the red, would be flat on the paper.
Right.
Oh my gosh, if you can see that, Ms. Quigley, that's really good, because that's really hard for people to see geometrically, but that was really good.
Yeah, I've been trying to learn this since high school. This is why I failed AP Chem hybridization.
Oh no.
So,
I'm feeling good about this semester though, okay?
yeah.
Good. So let's recap everything we've learned yesterday and today, because this will all be on your homework for tomorrow. Okay, so when you have a steric number of 2, we have now learned that that atom has to hybridize 2 of its valence orbitals. It always starts with the s, and once it hybridizes an s, it has to go to the p sublevel, so it hybridizes 1 of the p. So if you hybridize an s and a p, you're called an sp hybridized orbital. What's the geometry of sp hybridized orbitals?
Linear?
Perfect. It has to be, because linear comes from a steric number of 2. Does that make sense? Now, the one thing you have to keep in mind if you're going to draw pictures of this, because you should be able to draw a pair of sp orbitals along the same line, one to the left, one to the right. That's not really hard. But because we still have a couple of p orbitals left over in the outer shell of the atom, right? We're only hybridizing the px, not the py and pz. I'm going to need you to know geometrically where the py and the pz are, okay? So here, the 2 hybrid orbitals are the yellow and red, sp to the right, sp to the left, right? But I shouldn't have said that, it was bad, correct? But what else is in the outer shell of this atom that was not hybridized? The pz. And so, Ms. Quigley, I drew them both purple because that's just one big orbital that has 2 lobes, okay? So you can tell this is not a separate orbital up and a separate orbital down, where they're the same color. That just means it's a double lobe, dumbbell-shaped pz orbital. And this is an orange, it's a double lobed orbital as well that's on the y-axis. So a pz up and down, py coming out towards you and going back, and the 2 hybrid orbitals, as you just said on the left, are in linear fashion, one to the left, one to the right, okay? When you have a steric number of 3, you have to hybridize 3 of your valence atomic orbitals. You start with the s sublevel, you hybridize an s orbital, and then when you get to the p sublevel, you'll have to hybridize 2 of those, the px and the py. So to get to a steric number of 3, you hybridize s, px, and py, spp, sp2 hybrid orbitals. What's the geometry of sp2 hybrid orbitals?
Trigonal planar.
Yes, they are. and there's a p orbital left over because we didn't hybridize all 3 of the p's, there's a pz left over. Where is that pz orbital in relationship to the trigonal planar sp2s? Yeah, what a great question. Can you give me a one-word answer? Where's the 2pz in relationship to the plane of the 3 sp2s?
It's like going
down?
across it, right? Like how the orange one is in the linear.
So
Or no?
if the sp2s were flat on the paper, then the pz would be just like this, coming out and going back. Exactly. I would have said it's perpendicular to that. Okay.
Okay.
So if the sp2s are flat on the paper, this orange one is supposed to be perpendicular. It's sticking 90 degrees towards me and 90 degrees back. Just quickly, I'm going to draw it in a different perspective. I'm going to draw the sp2s as if they were on the equator. So you have to imagine that plane where the equator is. And then where's the leftover p orbital? It's north and south pole, so it's perpendicular to the equator. Does that make sense?
Yeah.
That's just 2 different ways to draw it. This turns out to be actually more helpful in a lot of chemistry to be able to draw it this way. But the other way, where the yellow, orange, and red are flat on the paper, and you just have the purple P pointing towards you and going back, completely valid as well. Okay. If you have an atom whose steric number is 4, that is telling you you have to hybridize 4 valence orbitals. That would be the s, the px, the py, and the pz. And so you would form sp3 hybrid orbitals. And because sp3 hybrid orbitals come from a steric number 4, they must be geometrically arranged as a tetrahedron. There will not be any p orbitals left over, so you don't have to draw anything else except for the 4 sp3 hybrid orbitals. And they, as you see in the picture, point to the 4 different corners of a tetrahedron. Okay.
And the angle between those is 109.5.
Tetrahedral angle of 109.5.
Okay.
Perfect. Then for steric number of 5, if you have to have a steric number 5, you're going to hybridize 5 orbitals in your outer shell, the s, px, py, pz, and then you have to go to the next sublevel, a d. They'll be sp3d hybrid orbitals. And because they're always for a steric number 5, they will point to the 5 corners of the steric number 5 shape, which is trigonal bipyramidal. And so if I show these orbitals here, every single one's a different color because these are now 5 different orbitals. I want you to look at this picture here and look at the picture above it. Wow, they really look the same. The only difference is I've drawn 2 purples here because this is just one single p orbital. There's only 1, 2, 3, 4 orbitals in this picture. This one, I've got 5 different colors because there's 5 different orbitals. 1, 2, 3, 4, 5. So similar in a sense, but technically different because these are 2 different orbitals on the up and down axis. That's 5 different orbitals. That atom can make 5 bonds. When you have a steric number 6, you have to hybridize 6 orbitals. So you hybridize the s, the 3 p's, and then 2 of the d's. That's how you get to 6. So those orbitals are called sp3d2. And these orbitals, because they come from a steric number of 6, will be pointing in the exact same geometry that we learned for steric number 6, which is octahedral. And so if you draw that, we're going to have 5 different orbitals pointing, 2 on the x-axis, 2 on the y-axis, 2 on the z-axis. It's going to look a lot like the picture at the very top, almost identical, but I have a purple orbital up and down. That's only 1 orbital there. And the orange orbital is only 1. So there's only 1, 2, 3, 4 orbitals here. This is 6 different colors because they are actually 6 different orbitals. They can bond to 6 different atoms. So if you go to a handout that you are looking at for shapes of molecules, I think it was handout 4, where the first page talked about shapes of molecules and depending on steric number and number of lone pairs. Second page of that handout gives you the relationship between sp hybridized atoms, sp2, sp3, sp3d, sp3d2, and their steric numbers. Okay.